Okay, so what I want to do today is I want to continue with the last of the applied lectures, talking about how can we use what we're going to develop in probability to actually solve real-world problems. One of the things that is terribly misleading about early math stats classes you take is the impression that you can often solve any problem. If you take an algebra class or a calculus class, you always have these nice exact answers. That is typically not going to be the case. It's also going to be unclear in many situations just what are reasonable assumptions to be taking for the problem, what are reasonable statistics to be looking at. And so we were talking about the German tank problem on Wednesday. And so here is a comparison of the estimates from the statisticians versus those from the spies. And again, you can't get the actual numbers during the war, but after the war, you can actually look at the factory records and whatnot. And you can see, it's not even close how much better mathematics and statistics did than the spies. Now, again, the challenge, of course, is when you're doing something like this, can you trust your results? Are the results reasonable? And can you convince the people above you that they should actually follow your recommendations? So again, it is not enough to just have the right answer. This is one of the places where Williams students have a competitive advantage when you're applying for jobs in finance or consulting. Do you actually have the people skills? Can you actually talk to people and get them to believe you? And I am happy to have greater conversations on that when things are not being recorded. So I will leave it at that for now. So we talked about the theory as to where the statistical estimate came from. We talked about some basic results in probability. We talked about some miracles of combinatorial identities that, with Pascal's triangle, if we summed along diagonals going from top right to bottom left, we had this beautiful result, which led to an algebraic simplification. And when we did everything, the dust settled, we got a nice explicit formula. If anybody here is jumping to try a generalization of this in a very different setting where you will have to come up with your own identity and come up with your own way of doing your algebra, let me know. I am running a small group, a summer research program in mathematics this summer. Happy to have people look at problems like this. The problem is you often need to have divine inspiration. You need to know, how should I look at this problem to see the algebraic simplification, to see how to get a closed form answer? I think I've mentioned this before. If I give you a quadratic polynomial, how would you find the roots? So what would you do? The first thing you would do if I give you a polynomial, say x squared minus 7x plus 12. Yes. I'm sorry? Try and factor. Your first is always the divine inspiration. Can I look at it and just see the damn answer? And if you can, great, there's the answer. And if somebody says, well, how do you know those are the roots? What would you say to them? If they doubt you for some reason, multiply it out. See, look, when I plug in this value for x and this value for x, it vanishes. Or I multiply it out and I get back the original polynomial. You can easily verify that you have the right answer. Unfortunately, let's say you're not divinely inspired, or I give you a nasty polynomial. What could you do to find the roots? Yeah, you could use the quadratic formula. And there's one for cubics, there's one for quartics. They get worse and worse and worse. But depending on what you're willing to do, you are able to get solutions to problems like this. And so, actually, let me see if I can just punch it up. I should have that from a talk I just gave. It's not like it's jumping around rather than punching. Here we go. So you're solving a quadratic equation is not that bad. You'll reuse the quadratic formula, not a big deal. Here are the solutions to the cubic. Just in case you've never seen them, it's probably worth seeing this at least once in your life. Is it hard now to solve a cubic if I give you this? No. You substitute. You write a script program, not a big deal. Do you think I got all the stuff correct in here? Do you think I made a mistake? How can you tell if I've made a mistake? Yeah, plug it back in, multiply it out, expand it. It's going to be non-trivial to do all these simplifications. This is the cubic. Here's the quartic. And the quartic gets so bad, I can only give you one of the 4 roots and still have it somewhat fit on the screen. So it is possible to write down explicit formulas for the 3rd and the 4th. Given this hint, you know how to find the roots of the quadratic, try to find the roots of the quartic, find the roots of the cubic. So just because we can solve a problem doesn't mean we can solve related ones. We want good procedures to allow us to move from one thing to another. And that's where I want to turn for the rest of the talk today, is to talk about how you might sniff out the formula for estimating how many tanks there are by gathering data. And I want to talk about how the data might initially be misleading and what we can do to try to clean things up. And this will be an opportunity to talk about linear regression, which we will do in much greater detail later in the semester. There are entire classes devoted to this. Basically, this goes back to calculus. If you have a nice function, locally, a nice function looks like a line. Lines are very easy to understand. So if we can ever reduce something to a line, it's not so bad. Turns out that we can handle generalizations of lines as well. The logarithm is a wonderful function because the logarithm converts many nonlinear expressions to linear. And we will see a lot about that later in the semester. Okay. So anyways, so the idea, and we'll do this again later, is to find the best fit line by choosing some parameters. So we believe y is linearly related to x, so y equals ax plus b. So if I observe xi, I'm sorry, if I choose xi as my input, I observe yi as my output. And I have 3 different choices of error. The first error is I look at the difference between what I observe and what I predict. The second is I look at the absolute value of the difference. And the third is I look at the square. One of these is right out. Which one is clearly a bad choice? Yes. Okay, why is the absolute value a bad choice? Okay, so do we want to have information as to whether or not the error is positive or negative? If I give you, say, 2 points, 1 point in the bottom left and 1 point in the top right, what is the best fit line that goes through them? So you would say the line that goes through them. Yeah, Professor Miller, 2 points determine a line, draw the line that connects them. Why is this a 300 level class? Well, if I take the line that starts in the upper left and goes to the bottom right, the 2 errors are of opposite sign and cancel. So the absolute value, it has issues. And I can absolutely understand that you might want to take into account, is our errors positive or negative? If I'm building an elevator, I'm concerned about weight. I might be concerned about which way I'm making an error. But when I'm trying to find the best fit line, if I can have errors cancel, I can actually adjust things to have a 0 error and be nowhere near the data. So the first one is actually the one that's not going to be used at all. So if I try to use the first one, I'm going to have issues. So now we're down to absolute value versus square.
Not a personal choice.
I almost said personal preference.
Yeah, just because it seems like the square would punish things that are farther away even more.
Yes, so the square punishes, so it's much worse to have 1 error of 2 than 2 errors of 1. Right. Right.
You have a lot of, you want something that's gonna punish like wildly.
So the question is, this is going to minimize maybe deviations from the line. Your average deviations may be smaller. But what if you just have 1 bad data point? What if you're collecting data, achoo, and you sneeze, and you completely misrecord something, or your mind just spaces out and you just have a bad data point? 1 bad data point will have a huge impact when we use squares. 1 bad data point will not have as much of an impact when we use absolute values. So if all the data is really, really good, it's not going to make much of a difference. But if you occasionally have a couple of bad measurements, a few bad measurements will have an incredible impact when we use squares. But there is an advantage the squares have over absolute values. So I teach this, the earliest I teach this at the college level is in multivariable calculus, where they've just done a whole year of calculus. And I like to try to tell my students, wouldn't it be nice if there actually was a reason why we made you learn all this material? That, you know, calculus could actually be used to do something? What's the difference between squaring and absolute values? The square is a differentiable function, the absolute value is not. The way I like to say it is if I'm hired as a consultant, I like to use the square because there's an exact closed form solution. If I am hiring someone, I want them to use the absolute value. So if we use calculus, we can actually get a closed form answer. So I'm going to just quickly sketch how you would do that. I'm not going to go through all the details. Oops, and I think I dropped a minus sign. I think it's the inverse of this matrix. Sorry. But basically, we'll talk about this in greater detail. If I have an error function and I want to minimize it, so I get to vary A and B. In one variable calculus, how do you determine if you have a maximum or minimum? What do you look for candidates? Okay, you look for places where the derivative is 0, correct? All right, so I'm going to put the iPad down. Please tell me when I'm moving my fastest, okay? They did try to have it on video and filming that. The iPad's been damaged too much to do that. Okay. Where was I moving my fastest in this room? Right before I hit the door? Right before I hit the door? Oh, I slowed down. I thought I slowed down as I hit the door, but basically it was at the endpoints. Do not forget endpoints. Right? When people are trying to maximize or minimize, they're always very good about saying, look for where you have critical points. Look for places where the first derivative vanishes. You also have to check endpoints. And the reason is if the first derivative is positive, you're increasing to the right, decreasing to the left, it can't be a maximum. Unless you're at the endpoint. It could be the maximum because you can't go further to the right. If you want to tell if you have a maximum or minimum at a critical point, what do you do? Yes, you could do the second derivative test. There's an apocryphal story, almost surely false, that when they were trying to build the stealth planes, they forgot to check if they were at a maximum or minimum. And at one point, one of the designs had the "I'm here" plane. Almost surely a false story that they were, at a minimum, not a maximum of stealthiness. For many things, we just need to know the candidates. So in one variable calculus, we find candidates by setting the first derivative equal to 0 or checking endpoints. Well, over here, you could see if A or B goes to infinity in absolute value, the error is going to go to infinity. So clearly, the minimum error is going to come from a finite value of A or B. So if we regard this as a function of just the variable A, we want the derivative with respect to A to be 0. If we want it to be a function of B, we want the derivative with respect to B to be 0. So we have both, at least a set of simultaneous equations. There should be, I believe, an inverse over here. And we get explicit formulas for the best fit values of A and B. And we'll do this in greater detail later in the semester. This is just a quick introduction right now. We will do this in much greater detail later. The point is there's explicit formulas for A and B. All right. Now, if we could only fit straight lines, this is kind of limiting because very few things in the world are straight lines. But the logarithm converts things that are not linear to linear. So if I write y equals bx to the a, and I take logs of both sides, then the log of y is a log x plus little b. And so now, even though big X and big Y are not linearly related, the log of big Y and the log of big X are linearly related. So this is why we give so much priority to logarithms in everything we do, because it allows us to use techniques again and again and again. We can linearize our data. So how many of you know Kepler's 3 laws of planetary motion? Okay, I've listed the third. Do you know the first or the second? No idea. High school? So the first is planets travel in elliptical orbits about the sun. The second is if you draw a line from the sun to the planet, it sweeps out equal area at equal time. So that means it's traveling fast as it gets near the sun than when it's further away. And then the third is the Sesame Street law. One of these laws is not like the other. Yeah, this is the one that's significantly longer and more mathematical. And it's absolutely amazing that this was discovered by Kepler looking at data. You want to talk about applications of statistics. If t is the orbital period, then t squared is proportional to L cubed, where L is the length of the semi-major axis. Absolutely amazing. So assume we don't know this. Could we discover this through statistics? Now, I'm calling my constant b tilde. Normally, you don't introduce a constant with a tilde. What does that make you think I'm going to be doing? Yeah, I'm going to be introducing a new constant, taking the logs. Actually, before I take a log, I'm going to take the square root of both sides, because I might as well set it up so that I have t to the first power. And so if I do that, I'll have t equals bl to the 1.5. So assume we don't know Kepler's third law. Could we discover this by looking at data? And again, we're going to do this in greater detail later, but here is a list of the semi-major axes of the planets, and I am measuring them in astronomical units, which is the distance from the sun basically to the Earth, and the orbital period in years. So if t equals bl to the a, does anybody have a guess of what b should be with this choice of units? Is there any planet you could look at that might give you an easy way to figure out what b is? Well, you got to give me one planet. What planet should I look at to figure out what b is? I mean, I could use any planet, except for the fact that I don't know what a is. That makes it a little bit hard. If I tried to use two planets, yes?
Yeah, you use Earth.
Yes, this is why I'm using astronomical units, right? I'm choosing things so that in these units b equals 1. There's a lot of interesting units in science. Has anybody heard of the Bruno, millihelen, slug, or smoot? Which one? Smoot. We might talk a little bit more about smoot either today or later. Slug? So I'll let you Google slug. Millihelen? Another interesting one to Google. Bruno? Bruno is similar to the smoot, and it's one of those units from the MIT students. It is, I believe, the indentation in cubic centimeters from dropping a grand piano off the 3rd floor of a given building. So MIT is responsible for some very interesting choices of units. Here's what happens if you plot the log of the period against the log of the semi-major axis. At this point, does it really matter if we use squares or absolute values to try to find the best fit line? We've got a line going through everything. This is beautiful. And when you look at the best fit slope and intercept, you get 1.49986.0001. Well, if my constant is supposed to be 1, the log of 1 is 0, so little b, excellent. And Kepler is saying it should be 1.5. I'm getting 1.49986. Not bad. Can somebody give me an explanation from physics as to why it might not be exactly 1.5? I'm sorry. So one possibility is bad measurement. So one is general relativity. We're doing a classical approximation. There's one other explanation as well. So Kepler's third law talks about the orbit of a planet traveling about the sun in an elliptical orbit. Why not? There's other planets, right? Which planet in particular? Jupiter. So you have some other planets in the solar system. What impacts do they have? So anybody know classically which planets were known? Earth, good. Mars, Venus, Mercury. 2 more. Saturn and Jupiter. Uranus was the first one discovered after ancient times. And it was one of the greatest examples of attempted ass kissing in the history of science. When Herschel discovered the planet, he decided to name it after his liege King George of Britain. The king was very happy. The rest of Europe said, hell no. And the compromise was, well, since Saturn is Jupiter's father, let's name the next planet Uranus after Saturn's father. So Neptune was then discovered purely by math. So in the 1800s, we didn't have rock stars, we had scientists. It was a very different world. And so the orbit of Uranus was a little bit off the predictions. And because it was a little bit off, there were two explanations that were floated. One was Newton's law of gravity was wrong, which no one wanted because it did such a great job in so many things. And the other one was maybe there's another planet. And if you have another planet that's far out, but close to Uranus, maybe it will impact Uranus and then fix a little bit of some of the issues in the other planets. And so there were a bunch of teams that tried to mathematically predict where Neptune should be. They used, in some places, I think, Bode's law about some kind of progression of where the planets are, which has no theoretical justification, but turns out to be right and help narrow their search because they have a bunch of free parameters. And in one of the greatest calculations of all time, they predicted where the planet should be. Now, the person who gets credit with the discovery may not have been the first one to predict it. There was somebody else, Adams, in England, but he couldn't convince the people to turn their telescopes and look there. So again, this comes back to what I was saying. It's not enough to be right. You have to convince people. I will send a wonderful article by Isaac Asimov on the discovery of Neptune. And then once Neptune was discovered and fixed the orbit of Uranus, they then turned to the other planets. And in particular, Mercury's orbit was off by a little bit. So imagine you've just predicted the existence of Neptune, fixes Uranus, the orbit of Mercury is a little bit off. What do? Well, you factor it in, it's still a little bit off. So what would you do to fix the orbit of Mercury? Try to find another planet. Where would you put that planet? Closer to the sun. They named it Vulcan. Yes, so the first occurrence of Vulcan in human writing is not from Star Trek. It is from a proposed planet in the solar system that would be just so damn close to the sun that it would really only impact Mercury. Oh, and it was always there? So there's also that possibility, but its orbit would have to be going at the same. It would be extremely hard to see. It's named Vulcan after the Roman god of the forge. And so they predicted where it should be. And now, unfortunately, since the planet is so close to the sun, it's going to be very hard to see. So what you need to do is you need to wait for certain types of eclipses, and that's when you have a chance to see it. And so they predicted when the next one would be, and they told people, turn your telescopes right here, right now. Stare into the sun, and you should see Mercury's fix, the planet Vulcan. And what do you think happened when people put their telescopes there? Some people might have gone blind. Most people saw nothing. And some people said, I saw it, I saw it. Well, when you tell people, I'm predicting something, oh, by the way, I'm the rock god who just discovered Neptune. Do you want to hitch your wagon to my, do you want to be known as the person who discovers Vulcan? How much can you trust the observational data? It is extremely hard. We talk a lot about bias these days. When you are looking at something like this and you believe that it should be there, does that impact how you view some of the data, especially when you're looking at really tough stuff? If anybody is familiar with Rutherford's gold foil experiments, where you often chose graduate students based on their eyesight and willingness to just stare for hours on end, you've got to be very careful about trusting some of this data. And so over time, most of the results were negative, and they kept decreasing how large Vulcan could be as the telescopes got better and better and better, until eventually Vulcan is only a few rocks that can't be enough to fix Mercury. And it wasn't until what you said earlier, general relativity, where you actually say the gravitational field under Einstein's equation equals mc squared, the energy of the field is equivalent to some mass that fixes Mercury and then goes on to fix everything else. Interestingly, the expedition that proved this was, I believe, a British expedition around 1919, but there was some concern because, we don't want to be proving a German theory of physics. What was this event shortly after? World War I. And most of the physics community was like, the hell you say, this is physics. It doesn't matter if this is German physics, Chinese physics, doesn't matter whose physics it is. Physics is physics. Is it right? But there were issues and concerns. All right, so when you see something like this, absolutely amazing. You could discover Kepler's third law just by looking at data. We're going to now see this for the German tank problem. I will just briefly say Smoot. I'll probably say Smoot again later because I love this story. So the Harvard Bridge is about 620.1 meters. Now, we no longer have fraternities on campus. I can talk to you off the record as to why. One of them decided to answer the following question. How many times would we have to pick up our pledge Smoot before we measure the entire length of the bridge? And they got 364.1 Smoots, and I love this, plus or minus 1. So they actually put down paint markings every time they picked him up. Cambridge did not find this amusing, and they had the paint markings removed. Well, the fraternity wasn't pleased with this, so they took Smoot and they did it again. Yep, they would lay him down. Yep, pick him up, lay him down, pick him up. Eventually, it got to the point where the city of Cambridge said, fine, just leave the Smoot marks. It's now become institutionalized. And if there is an accident on the bridge, they report at how many Smoots on the bridge did the accident happen. It's been formalized. It's absolutely wonderful. I will mention a little bit more of Smoot at the end of the day. I'm going to skip the birthday problem because we've talked about that already. But again, you can see, well, I'll just at least do this so you can at least pause the slides. By the analysis we did at the start of the year, we had d to the 1/2 square root of log 4. If you try to do a similar best fit, when you do this, I did 2 different sets of 10,000 simulations, and I get the exponent of d is 0.506 the first time, 0.481 the second time. So again, you can sniff out these exponents by doing these fits, and it doesn't have to be linear. You can take logarithms. I'm not going to go too much into this picture here. If I try to look at the German tank problem, I've got a few more things going on here. So it's not a standard linear regression. I've got an extra parameter that I'm fitting, and I'm plotting n against the log of m and 1/k. And you see, it really does look like a plane. All right. What I want to do now is I want to talk a little bit about implementation issues with trying to find the best fit line. And again, we are going to talk about this again later in the semester. Since this is one of the most important things we're going to do in the class, I want to do this twice this semester, once now and once again later. In terms of marketable skill sets from taking probability, being able to do a linear regression, being able to linearize data and do something like this, it's one of the most valuable things you can do. It's worth seeing twice. So here, I am plotting n, the number of tanks versus the maximum observed. And I'm fixing the number of tanks to be 1. So theory said n should be 1 plus 1/km minus 1. The minus 1 doesn't really matter. So I should get n is 2m minus 1. And I'm going from between, say, maybe 1,000 and 10,000 tanks. And I get my best fit line is about 0.784m plus 2,875. Could this formula hold for all values of m and n? Do we expect this to hold for eternity? That the number of tanks we would predict should be about 3/4 m plus around 3,000. Okay, why are you concerned? There is a good reason as to why this is bullshit. Like some of the calls the umpire made in the game we played yesterday. Yes. What do you know about your estimate for the number of tanks? So you have to remember back to Wednesday. What kind of results do we prove about how many tanks there must be? I'm sorry? Has to be at least one, but we can do better than at least one. We observe k tanks starting, the tanks go from 1 to capital N. We observe k of them, and the largest serial number we observe is little m. So what can you tell me about a lower bound for the number of tanks? It's at least m, right? So as we go further and further and further, could this equation possibly be true? No, there's no way this can be true. And the reason it's not true is I basically flipped my axes in what I'm doing. How do I do things? I'm choosing capital N, And then I'm randomly drawing one tank from that and recording the value of M. And then I'm using that M to predict N. I should be doing it the other way. I should be plotting N on the x-axis and M up here. So the point of this is to show that if you make a really small mistake in terms of which way you view things, you can get something completely absurd, but hopefully you can recognize that it's absurd. So I'm not choosing M and then having N come from that. I'm actually choosing capital N and doing my simulation. If I go up to 2 tanks, then theory says it should be 1.5 M minus 1, and I get 0.964 M plus 1424. It's better, but it's still wrong. If I go up to 5 tanks, I at least it's like the sound barrier. I at least finally crack 1.000 M. So there's at least finally a chance that this is a reasonable result. Notice that we don't seem to have as much of a spread as we keep going higher and higher and higher. You know, that this looks worse than this, that looks worse than this. It seems to be getting a little bit tighter. All right, but this is not great results. Now, if I do it the other way, if I plot on the x-axis as my input variable the number of tanks, and on the y-axis my output variable the maximum observed, you know, I still have a decent spread, but theory says it should be, little m should be k plus 1 over kn plus k plus 1 over k. So about k plus 1 over kn. And now I would get, when k equals 1, about 0.5 n. And the best fit line is 0.496 n plus 10.5. That's really good. And so when I actually plotted in a way that's similar to how we're doing the experiment, where the x-axis is the number we're sampling from, is the input, we're getting a good job. If I go up to k equals 2, the slope should be 0.667 approximately. I get 0.668. You know, really hard to argue with that. If I go up to 5, I get 0.883 approximately is the prediction. I'm getting 0.828. And again, we got a little bit lucky with having such a great fit over here. If the fit is too good too often, you should be suspicious of the data. You know, some amount of fluctuation is reasonable. This is a reasonable amount of fluctuation. And so when we look at this, we seem to be able to predict the relationship. So if you give me a k, what I'll do is I'll choose a bunch of n's, record the maximum observed, and use this to get a formula. And so now if you give me a k, I can just go to one of my simulations. All right, that's nice, but that means I have to do this every single time for k. I want a formula as a function of k. What I have to do now is somebody tells me, we just observed 17k, which formula should we use? All right, here's my formula for 17k. Whoops, we observed an 18th. All right. It would be nice if we had a formula that took as inputs m and k and output the best guess. What we're doing here is we're getting a bunch of snapshots. Here's the k equals 1, the k equals 2, the k equals 5. So before I go into the generalization of how we try to get the formula as a function of k, here's one other thing you could do. I'm going to average 100 runs for each n. And so over here on the x-axis, I am keeping my maximum observed. And on the y-axis, I'm now keeping n. So this is not the way we really should be doing it. But if we do this nice little trick, notice how much the fluctuations die down because we're averaging. And now instead of getting 1.5 m minus 1, we get 1.496 m plus 171. Much more reasonable numbers than the roughly 3/4 m plus 3,000 we had before. So the general principle is a lot of times averaging can cut down on a lot of your issues. All right. So what I want to end with today is trying to see how can we sniff out the k dependence. So here is a plot. On the x-axis, the number of observations, that's our k. And on the y-axis, what I'm doing is I am plotting the best fit constant in n equals am plus b. So a is really a function of k. And b is a function of k. I'm doing the best fit line where a and b are functions of k. And I'm recording what the result is. Now, does it seem reasonable that as k gets larger and larger and larger, the best fit n is just a little bit more than m? Yeah, I mean, if you start observing a huge number of tanks, odds are pretty good that your largest observed serial number is close to the best. When we start off with a small value, it's not surprising that we're off by a bit. All right. Can anybody look at this and see the functional form? All right, so one guess is it could be e to the negative k. That's at least something that's going to decay. But decay at what rate? Is it decaying like e to the negative k? Is it decaying like 1 over log k? Is it decaying like 1 over k squared? 1 over k log k? It's hard to look at this. Well, theoretically, we know the answer. It's supposed to be 1 plus 1 over k. So if we subtract 1 from all these values, we basically have the hyperbola xy equals 1 or y equals 1 over x. So does this kind of look like, if I just forget about the 1, does this kind of look like a hyperbola? It's not unreasonable to be thinking hyperbola when you see this. But again, my eyesight is not good enough to really distinguish between 1 over k, 1 over k log k, maybe even 1 over k squared. One of my colleagues accidentally responded to a letter with the wrong name for somebody. He called them Ellis, their name was Elias. Why do you think he called them Ellis rather than Elias? That's a possibility. How do you write Elias? E-L-I-A-S. How do you write Ellis? E-L-L-I-S. An I and an L, as you get older and your eyesight gets worse, can be very hard to distinguish. Do you trust your eyesight enough to see a difference like that? Especially if it's pre-coffee, as you get older, right? When you look at this, this is even worse. We're not trying to distinguish letters. We're trying to distinguish mathematical dependencies. How confident are we about looking at this and seeing exactly what the relationship is? So what could we do to maybe have an easier set of data to look at? We could linearize it. And so how do we linearize it? So start taking logarithms. So we have two possibilities. We could take the logarithms immediately, or I could subtract 1 first and then take the logarithm. Let's subtract 1. The reason we're subtracting 1 is we know it has to be at least as large as m, right? If we observe m tanks and they start with tank 1, there has to be at least m tanks made or in the field. So let's just subtract off that known information. And so we'll plot the log of a minus 1 against the log of k. And here is my plot. What do you think? I'd go a little bit stronger than pretty good, but I'm a little bit biased as I'm one of the authors. I think this is phenomenal. When you're trying to see this linear relationship, that is one hell of a fit. And what do we get? If it was exactly 1 plus 1 over k, we subtract 1. What's the log of 1 over k? So the log of 1 over k is what? So it's negative log k. So if we take the log of a minus 1, that should look like negative log k. So we're plotting negative log k against log k. What should be the slope of that line? Negative 1. We get a slope of negative 0.999. Does 007 surprise you that he would play a role in World War II? Cultural extra credit. When was the first Bond movie? Could be. I'm not sure. I know it's between, I think, 61 and 63. Is it 61? Goldfinger could be 63. Goldfinger was the third. Dr. No was the first. Second? I think it was From Russia with Love. So there were 3 things I wanted when I was getting married. One of them was that we played one of the James Bond themes as people were coming into the temple. And so we played the theme All Time High from Octopus. And as my friends were coming, wait, that can't be. No, they're not playing a Bond movie, are they? The 007 is, of course, entirely coincidental. But look at this. This is gathering data from simulations. We don't know that it's supposed to be 1 + 1 over k. But we do a couple of simulations. We record the best fit values from these. We analyze them, and it predicts that the relationship should be n = 1 + 1 over km. We got the slope just by looking at this. So by looking at a couple of key values for k, we found a way to generalize. This is absolutely amazing. And so again, I'm doing the course a little bit differently this year than previous years. I wanted to show at the start of the semester just how powerful these tools and techniques are. A lot of people are afraid and they don't necessarily apply for fellowships because they feel, I don't know enough. You don't need to be able to solve a problem fully. What you need to do is do a better job than is being done. That's a much lower bar. You just have to add value. And if you can do a couple of basic things, this is why you had no homework for a week, no written homework. This was an opportunity to read ahead in the book and to master your programming so that you have these skills. And with these skills, there are so many things you can do. All right, so some references, but I want to just mention one of the pieces of advice I always give students. So I always tell you, seize opportunities. You should get to know at least one professor well. So when you make comments in class, you're supposed to be emailing me, hey, professor, I made this comment. It's a great way for me to get to know you. If I need to write a letter of recommendation, it's a great way for me to make it specific. It's also a great way to get you comfortable speaking up in class. So many people are extremely talented, but they don't always get the credit they deserve because they're a little bit shy and reserved. And other people end up getting the credit. And so I want you to get in the habit of speaking up. It's hard. When I was an undergraduate, I did not like speaking up. I always find it amazing that I've ended up as a professional lecturer in some sense. Best thing that happened for me in grad school was when one of my friends told me I should run to be a social chair for the graduate school. And I said, normally you want somebody who likes to be with people and is an extrovert to be in a position like this. Are you really sure that an introverted mathematician is the best choice? But it was one of the best things that ever happened. It really got me out of the shell. Seize opportunities. I'm happy to be one of the people you get to know well this semester. I deliberately do not try to get to know my students because that's not how the real world is going to work. Your boss is not going to come up to you and really try to get to know you unless you're really lucky. You have to learn how to get noticed. So I will provide plenty of opportunities, always up for a walk, for coffee, for a meal. Treat is on me or Williams College, depending on whether or not the coin lands heads or tails. But seize the opportunities. If it's not me, get to know other people so that when we have opportunities, we know, hey, this would be a good fit for you. Or when you need a letter of recommendation, we can write one that will actually be meaningful. All right, so we mentioned Smoot. Smoot fortunately survived being a human walking stick. Does anybody want to guess? If you know the answer, you're not allowed to answer. Does anybody want to guess what happened to Smoot professionally? He started making rulers. You're close. He became the chairman of the American National Standards Institute and president of the International Organization for Standardization. You cannot make this up. So imagine you're Smoot. You can imagine that it may be a little bit embarrassing, degrading, whatever, to be used as essentially a large meter stick. Or you could just roll with the punches and just have fun. So the problem is the Smoot is not well defined, because as he grows and changes, it's actually a really interesting question. How do you define fundamental units such as meter? Anybody know how the meter was originally defined? It was a specific bar of metal. I think it was in Paris. Yes, you would have to bring your own bar. And of course, it could matter, what is the temperature? What is the humidity? Could matter maybe how high you hold it. How do they define meter now? It is the distance that light travels in a certain amount of time. So now you have to define time. How do you find time? Yeah, it's something it's from cesium. I don't, it's 130 something. 137. So it's, in terms of, vibrations or energy transfers of, cesium atom. And so the second is now the fundamental quantity. And because the speed of light is a constant, then we define length through that. So it's not always easy to come up with, what is the right definition. For using a Smoot, his height is not going to be constant. And again, you can imagine it would be a little bit annoying if people constantly coming into his office saying, I'm sorry, I need to compare my portable smooch to you. So you need something a little bit better, but he could have taken this so many different ways. But I could only imagine the stories he would have as he's applying for positions and whatnot. And the fact that his name is going to be known. The first winter study class I ever taught here was on cryptography, and I encrypted the title of the class. And the college asked me, are you sure you want to be the title of your class and that to be on students' transcripts? I said, absolutely. It's going to be a conversational starter. And several of my students came up to me and said, Professor Miller, you were right. When I was being interviewed, they said, what the hell is this class? You want ways to turn the conversation to points that are your strength. When you are having an interview, what would you like to talk about if you had the opportunity? All right, so this is a good place to stop for today.